of things. The first thing that I want to do is just revisit this problem number 65, because what I did for you the other day was I solved a bunch of generalities that would have been true for a whole bunch of problems that were set up in a similar way to this. The generality is we have something sliding down a slope, and then it changes, like there's a change in the slope. It goes from one angle to a different angle, and then it keeps sliding. Okay, that's the generality. Some of the specifics here are that angles, like one of those angles was 25 degrees, the other was 0. We had some information like the coefficient of friction on the flat part, and we knew that there was no friction on the part that was sloped. And we knew one other thing as well, which was, and I didn't write this down because we didn't need this yesterday, but we need it today, and that is that the length of the sloped part is 3 meters. Okay, so there was 3 meters of slope, and then what we were trying to find, another one of the specifics was how far does this sled and the person on it travel, okay? So where we ended up was here. We figured out that we needed 2 free body diagrams for this. I used 2 frames of reference as well. You don't have to. You can use the same frame of reference for both of these. It'll work fine. But as I've mentioned a bunch of times, when we have objects on slopes that are moving along the slope, the easiest way to approach it is with an angled frame of reference, because at least one of your forces, if not 2 of them if there's friction, will be aligned with an angled frame of reference, and all the motion is aligned with an angled frame of reference. When the slope shifts, now all of our forces and our motion are aligned with a standard vertical and horizontal frame of reference. So it makes a lot of sense to switch frames of reference. We also have 2 free body diagrams. This isn't optional. The frame of reference changed here because I chose to make it change. I didn't have to do that. The free body diagrams changed because the forces changed. If you look at what's happening on the slope, we have one force that's perpendicular to the slope, one force that's vertically down. When we look at what's happening off the slope, we have a perpendicular up, a perpendicular down, vertical up and vertical down, and a horizontal to the left, the way I've drawn it. Those are completely different forces. No matter what we do, we're going to have 2 free body diagrams here. The forces acting on the object on the slope are different from the ones acting on it when it's straight. Some of those forces are the same, namely the weight, right? The downward force from gravity does not change. The direction and the magnitude of that force are constant, but the normal force changes in direction, and we can actually see here, it changes in magnitude as well. If we look at this equation, the normal force on the slope is going to be equal to the weight times something, the cosine of the angle, which is going to be less than 1, which means the normal force is less than the weight of the object when it's on the slope. As soon as it's on the flat, the normal force is equal and opposite to the weight. So the magnitude of the normal force changes, the direction of the normal force changes, and we didn't have friction on the slope, and we do when it's on the flat. So we have new forces. We have to have separate free body diagrams. That means that when we start adding up our forces and thinking about the sum of forces and how they're equal to mass times acceleration, we have different forces, therefore we have a different mass times acceleration. The mass stays the same, so our accelerations are different. We have 2 different accelerations here. This acceleration is on the slope. This acceleration is on the flat. It doesn't accelerate at the same rate. And if you think about it logically, you didn't need to look at free body diagrams or even think about physics to figure that out. You know what's going to happen here. He starts at rest, he starts sliding. he is obviously accelerating down the slope. He's speeding up. As soon as he hits the flat, he slows down and stops. That is a acceleration in a different direction. It may be the same magnitude, we don't know, but it's definitely in a different direction. The acceleration has to change. And that seems weird, because it's like, well, it's the same object, but the same object in two different situations is gonna behave really, really differently. This sponge, while I'm holding it in my hands, is experiencing one set of forces that's resulting in no acceleration. When I change those forces, it accelerates downward at about 10 meters per second squared. So changing the circumstances can change forces, which can change acceleration of an object, all right? So let's look at how we can take this scenario and actually like get some information and come up with some hard numbers. So first of all, there is some math here that's gonna be a little bit, we're gonna have to use some math, okay? And the biggest thing here is recognizing that we have an acceleration for the downhill part that's equal to g sine theta. And sine of theta is just a thing that you've got to be able to use. So on your calculator, it's going to look different depending on what kind of calculator you have. When I use this calculator, I have to kind of go about things a little bit backwards sometimes. So like if I choose sine, it tells me the sine of 0. And that's not what I want. I want the sine of some sort of an angle. So if I put 25 in and then I choose the sine function, then it tells me a number, and that number is this, like, that's the sine of that angle. The sine of 25 degrees is 0.4226, okay? And so, what I want you to think about here is your calculators are going to be a little bit different than mine, and so I don't know how exactly you're going to use your calculator. Some of them you type the sine function first and then the angle. Some of them you type the angle first and then sine. In this case, now that I've typed that in, I can multiply that by g. What's g? G is 9.8 or 10. It doesn't really matter. We're going to get something pretty close to the same thing no matter what we do. About 4.14. Could we use all of these? Yes. Is it going to materially change anything that we do? No. In fact, I'm just going to use 4.1 because I might be a little bit off by like some fraction of a percent, but I don't really care. So I now know that my downhill acceleration is going to be about 4.1 meters per second squared. And that's in my positive direction. We did all the math to include the signs. So this sled plus Josh are gonna accelerate down this ramp at 4.1 meters per second squared, starting from rest, which means after 1 second, they'll be traveling 4.1 meters per second. After 2 seconds, they'll be traveling 8.2 meters per second or so. And because of that predictability, we can figure out how long it would take to go 3 meters. We can figure out how fast he'll be going at the end of 3 meters. And you'll see in a second that that's what we're gonna need, okay? On the flat, the acceleration is gonna be negative mu k times g. So what's that? Well, mu k is 0.05. So, did I get rid of my calculator? I got rid of my calculator, that was clever. So mu is 0.05, g is 9.8, so it's about 0.5, right? That's good enough. And it's negative, so it's about negative 0.5 meters per second squared. What does that mean? Well, that means if they started at rest, that they would start to accelerate to the left, but that actually doesn't make sense because it's friction that's providing the leftward force. If Josh and the sled are sliding to the left, then friction is going to be to the right. So what's going on here? What's going on here is this will be the constant acceleration as long as the cart is moving to the right, which it is. When he gets to the bottom, he's moving to the right. friction is to the left. So there's going to be a constant force to the left causing this constant acceleration. What does that tell us about speed? That tells us that after 1 second, Josh and the sled will be moving about 0.5 meters per second slower than they were at the start. After 2 seconds, they'll be moving 1 meter per second slower than they were at the start. And then after 3 seconds, 1.5 meters per second, until he stops. At that point, his acceleration is going to drop to 0. You're not going to keep going to the left. It's not a rubber band. Friction doesn't accelerate you, make you go faster in one direction. It slows you down. Once you're at 0, you can't slow down anymore. Okay? There's still friction, maybe static friction, but it's not going to be anything that slows you down because you won't be moving. So how do we get from this to our unknown of x? Well, the way we get here is by going back to our previous system. What was our previous system with kinematics? We start with what we know. We make a drawing. Well, I already did that. We identify variables that we know. We have 2 parts to this problem. 2 different accelerations. One here, one here. That's 2 kinematics problems. Kinematics equations only work with constant acceleration. So we can do something with what's going on the slope and something with what's going on the flat. We can't combine those together into one problem. So let's look at on the slope first. We're going to have some initial position and some final position. We're going to have an initial velocity and a final velocity. We've got an acceleration and we've got an amount of time. And let's say that this is our position 0. And that means, since the slope is 3 meters long, our final position is going to be 3 meters. So our initial position is 0, final position is 3 meters. So we've got this worked out. The problem says Josh starts at rest, so our initial velocity is 0. We don't know our final velocity. We do know our acceleration. It's 4.1 meters per second squared. How do we solve this? With the vector solver, with the kinematic solver. We've got the kinematic solver. Our initial position is 0, final position is 3, initial velocity is 0, acceleration is 4.1. And we could find either the amount of time that it takes, 1.2 seconds. Of course, it's not that that's wrong, it's just that's not super helpful. Or we could find how fast he's going at the end. That might be kind of helpful. If we know how fast he's going, then maybe we can use that to figure out how far he's going to go once he's on the flat. So he's going about 5 meters per second at the end. So let's start with that and see where we get. Now, I happen to know this is the right way to approach the problem. You might not, but you could have found the time too. So we know his final velocity is 5 meters per second. The time is 1.2 seconds. Now let's look at what happens on the flat. We have a different frame of reference here. Let's call this starting position 0. Our final position, we don't know. In fact, that's what we're trying to find, is how far he goes, right? So our initial position is 0. Final position is unknown. Our initial velocity, we're not told what his initial velocity is. He's not starting from rest. But we figured it out, didn't we? This is how fast he's going. Now, some of you might be like, wait a second, something's going to happen when he hits the bottom. Like, something is going to shift. And you're right, something would shift. This problem doesn't work out exactly as it's described. But this is all we have to go on. So we're going to say his initial speed is going to be 5 meters per second, because it's going to be about the same as it was when he got to the bottom. His final speed, well, we're not told what that is either, except we know what it is, because we want to know how far he goes before he stops. Stopping means 0. Our acceleration, we know that. We figured it out with the forces. It's -5 meters per second squared. The amount of time that goes by, we don't know. We could find it, but now we know we don't need to. This is what we're looking for. And we have 1, 2, 3, 4 pieces of information that we could potentially use to find it. So let's see what we get in the kinematic solver. Our initial position is 0, final position is unknown, initial velocity is 5, final velocity is 0, and our acceleration is negative 0.5. We could find time. It's going to take about 20 seconds, okay? But we don't need that. What we want to know is how far. And we can find that using this equation. It looks like 25 meters. And this is typical for the book to use a bunch of numbers that end up kind of being easy, right? Like this was really about 4, negative 0.5, 5 meters per second, like 25 meters. That's relatively typical for the kinds of made-up problems that you see in the book. When we do work in here, we're using real-life things, so we can't count on things being as nice and neat and clean as that. But what you can count on is that there's wiggle room, there's variation, there's error in all the information that we get, and that means that that it's okay to like round things. It's okay to be a little even. You can be sort of heavy-handed with the rounding, and we're not going to need more than 1 or 2 significant figures. For those of you who remember that from chemistry, we're just not. Not because you get the same answer either way, but because it's not any more meaningful to use more than just a couple significant figures. All right. So so this is the like rest of problem whatever that was, 65 or whatever it was. And what I want you to see here is the connection between the forces part of it and the kinematics part of it. And this is a pretty complicated one, and I wanted you to look at this on purpose because I want you to see, like, there is no way that I could have prepared you for this problem without giving you this problem. Just like there's no way that I can prepare you for the next 2 homework problems that I'm assigning for you for Thursday without giving you those problems. Just like there's no way for me to prepare you for this situation without having you do this situation. Everything is new. It's the same basic idea. Free body diagrams, resolve forces, set up Newton's second law, and if there's kinematics or friction or whatever, bring in your other equations as needed. The general idea is always the same. The specifics, no matter what we do, there's always a problem that we've never seen collectively. If you all were to scour the physics text, you could easily find a problem that I have never solved. And if you gave it to me and asked me to do it in front of the class, I might not be able to. I might get stumped. But like I said, I kind of think that would be good for you to see. But so if you want to, go for it. Like, I enjoy that kind of challenge. I think it's really fun. And I think it's really, in particular, fun when I get stumped by something that you get to see. Because I love that. I love for you to see me be like, wow, I understand a lot of this, but I can't figure out this next step. And then usually what I do is I go try to figure it out on my own. I won't look it up. I won't look up the solution. I will crack it because I know I can. But it may take me a while. Okay, so here's where we're starting today. What I am going to ask you all to focus on, this doesn't mean you're limited to this. You should do like whatever you can. But what I'm asking you to focus on today is kind of some preliminary stuff having to do with the lab. So on yesterday in class, I asked you to read through the lab, to just read through it, and I hope you did. If you didn't, it's worth reading through it so that you can see. Oh, that's not what I wanted to do. So that you can just kind of get a feel for the overall process. It's complicated. There's a lot. But I also am going to try to break things down for you in a way that will make it a little bit easier. So what I have laid out for you to do today is to make some free body diagrams for the cart and the hanging mass. Many of you have already done that. I want to see those before you go any further. And some of you should be prepared that I'm going to ask you to do more. because some of you, I'm not 100% confident that you have the whole free body diagram thing nailed down. And then I want you to think about how you can find the force of friction that's acting on the car. You need to know how much friction is acting on your car. The force of friction will change with the angle of the track. You figured that out when we were exploring friction, when we were doing the investigating friction activity. So if you have your cart at a real shallow angle, it will have some amount of friction. If you have a steeper angle, it's going to be some different amount of friction. You should be able to find it no matter what the angle. If I ask you to find the amount of friction acting on a cart with a block of metal in front of it and a block of metal on top of it in any situation, you should be able to find that force, okay? And then, based on that force that you found and some other stuff that you know about friction, you can find the coefficient. Remember what I told you about the coefficient. It's unique to the surfaces. The surfaces aren't changing. The angle can change, the normal force could change, but the surfaces that we're talking about are not going to change, which means if you find the coefficient of friction for any one situation, you now know the coefficient of friction for every situation. And with that information, if you know the angle of a ramp, if I tell you, fine, now we're going to put it at 12 degrees, you can tell me how much friction will act on it. If I say, nope, I changed my mind, 31 degrees, you can tell me how much friction will act on it, because you know the coefficient. That's why having the coefficient is handy. And then once you get to the point where you're like, okay, I get it, I know how I'm going to do this, then you can and should start collecting data. So your goal today is to at least make a significant amount of progress towards knowing what the coefficient of friction is. That's part one, so to speak. If you don't know the coefficient of friction, we can't make any predictions down the road. Once you've got the coefficient of friction, then we have some ammunition that we can use to make all sorts of predictions. Then we can figure out all the forces that are going to be acting on it at any angle and with any amount of mass on the cart, for that matter. And then with that information, you really are good to go in terms of making predictions about how much force it will take to make you accelerate at a certain rate, right? So this is kind of how I view your job. You're not limited to this, but this is my recommendation for how to approach it. Does anybody have any questions before we get started? Okay, you may have missed this, but I said there is another homework assignment. We'll go over that on Thursday. It's a couple of problems, and there's some challenge in there as well. And those of you who, if you recognized yourself in the stuff that I was saying at the start of the period, don't panic, just do stuff, right? Like, that means you need to be really thoughtful, and it means you need to be practicing. Be thoughtful and practice. That's how you're going to achieve mastery of these skills. Okay, you guys have the rest of the period to get some stuff done.